questions before we start? No specific questions? Are you ready for the quiz in a moment? Okay. So, I do want to just mention one thing. In the email that I sent out the last night, there was an error that I said there could be problems involving limits that involve with sine x over x. That's what I meant, not 6x. That's pointed out by Hunter. This letter will somehow type the x instead of n. Yeah, I really meant the sine x. All right, let's start with our lecture. So we did a 2.6, which was implicit differentiation. Then we jumped to 2.8, which was related rates. Okay. And we skipped to 2.7, which is rates of changes. We may or may not get that. But so for now, we're skipping that. Let's move to 2.9 today, linear approximations. So linear approximation is a way to use a straight line to approximate a function y equals fx. Okay? Let's see how this should go. The picture should show you the whole idea here. Now notice that I draw two different pictures, and it's actually a little bit confusing to begin with. You can argue both pictures could work. Okay. The first picture is the picture we use when we are trying to compute the f prime at point A. Remember that? So remember we try to compute f prime at A, and that was hard to compute. Basically, f prime A is supposed to be the slope of the tangent line at the point A, and that was not easy to do. So what we did was to take a secant line from point A to point X, and then let X approaches A and take the limit as X approaches A. So this was defined to be the limit as X approaches to A, and take a slope of the secant line. And slope of a secant line going from this point, which was X equals A, Y equals FA, right? This was the first point. And second point is x equals x, y is equal to fx. All right? And we have those 2 points, and there's a well-known formula that tells you the slope of the line segments connecting the 2 points, which the formula says y2 minus y1 over x2 minus xy. Okay? In this case, it becomes fx minus fa over x minus a. Okay? Fx A divided by x minus a. This was a way to compute the slope of tangent line at this point. And what we're focusing here is slightly different. We want to compute the approximate value of fx. So here we want basically we want a slope of the tangent line. We want a slope of the tangent line. Which is also called f prime A. Over here is different. We want the approximate value of fx. Value of fx. All right. So the picture here does not really help, because if you sort of take the secant line, this goes back to fx. And look at the picture here. What we do is to take the secant of taking the tangent line, use that to approximate my function. So fx is usually hard to compute. What we can do is to compute this value, which is almost fx. Okay. So if you label this to be P, a point P, a point Q, a point R, basically we use R to approximate the Q. So we use the point R to approximate the point Q. You can actually compute exactly where R is. Okay, let's do both. So let's do the coordinate for P, Q, and R. What is the coordinate for P? X equals to A, and what is the Y coordinate equal to? FA, right? So P is simply A, FA. That's easy. What's the point of Q then? What's X? X coordinate is just X. And what's the Y coordinate? It's Fx because it's on the curve Fx, right? So Q is X, Fx, all right? And what's the coordinate for R?
X.
X coordinate is X. Y coordinate is something you have to compute. Okay? Let's try to figure out. So here we have this straight line here. Can you tell me the equation for this straight line? Oh, we know a point. This is our point. We know the slope. What is the slope? The slope is m equals to f prime a, right? So m is just f prime a. That's the slope of the line. Given that, we should be able to write down the equation. What should be the equation? The equation would be something like y minus y0, which is fa, equals m, which is f prime a, times x minus a. Are you with me? Therefore, y equals to that plus fa. So let me write down the result. Y is just equal to fa plus f prime a times x minus a. Okay? Don't you agree? This is the equation for that straight line. All right. And now we are going to use this point R to approximate the Q. So what's the y coordinate for R? That's exactly this. So R, if you want to write down, it is just fa plus f prime a times x minus a. We're going to use this to approximate the Q. That means my fx is almost the same as that one. We're going to use this to approximate the fx. Right? So we have the following approximation, which is fx is approximately equal to fa plus f prime a times x minus a, right? That's the approximation. This is called a linear approximation. Why is this called a linear approximation? Because we're using a line, a linear line, to approximate a curved function. That's called a linear approximation. And once again, this is worth to be put in the box. So this is the main formula for this section. Let's see how this formula can be applied. So I'm going to erase this picture. This picture is no longer relevant. Remember, this was the picture that defines the derivative slope computing and slope of hanging line. And this is really the picture that is relevant for the current section. Okay. So let's do an easy example. Let's suppose we want to compute approximate value of square root of 101. Okay. Well, it's not obvious what this number should be equal to, right? But if you look at this number, you would say, well, this is almost the same as square root of 100. Okay. Square root of 100 is an easy number. That is equal to 10. So you may want to say, well, this is the same as, this is almost the same as 10. Okay? That is some kind of approximation. But that would be kind of using P to approximate the Q. So instead of say fx, let me just say fa. Okay? But we can do better approximation. We can do better than that. So what we're going to do is to use this as a straight line to approximate that. Okay. So to do that, we need to apply this formula. To apply the formula, we need to define the function fx. And then we need to decide what a is and what x is. Right? So what is fx? That would be square root of x, right? Is that more or less obvious to us? Usually the choice is obvious. Okay? So let fx to be square root of x. Okay? That also decide what a should be. Well, a is usually a simple number that is nearby. So in this case, you choose a to be 100. So a is 100. And let's also decide what x should be. Or x should be the one that we are working on, which is 101. Okay. So 101. And we apply that formula to this. So you want to know what square root of 101 is. So in other words, you want to compute the fx. The formula says it's approximately equal to the expression on the right. To do that, we need to compute what is fa, what is f100. Okay. So what is f100? That is just the square root of 100, right? Okay. And that is obviously just equal to 10. Right? Let's also compute f prime at 100. Well, first you compute f prime x. Well, you can easily compute f prime. First you write f in the form x to the 1/2. So f prime x is just a 1/2 x to the negative 1/2, right? So you substitute 100 into this, therefore 1/2 times 100 to the negative 1/2. And that gives you 1/2 1 over square root of 100. Right? Negative 1/2 is the same as 1 over the square root. And that gives you 1 over 2 times 10, 1 over 20, right? So this is equal to 0.05. All right? So now I can apply the formula. F100 is approximately equal to, F101, sorry. Approximately equal to F100 plus F prime 100 times x minus a. What's x minus a equal to? That's just equal to 1. Yeah? Question? I mean, I can write 1 over 1 minus 100, but it's going to be 1. Okay? And that will give you some number. So in this case, it's 10. 0.05 times 1. So the answer is 10.05. 10.05, that's right. So you can say 10.05 is an approximation of square root of 101. And this is supposed to be a better approximation of just the 10, which we got first. Okay. I feel like I can give you a real life example. Let me give it a try. Okay, this is very much like a textbook example. You see that in every textbook. Let's think about the following situation. I have this experience quite a lot. Suppose you're driving on the highway, okay? You drive from A to B. A to B is 60 miles. And you drive at 60 miles per hour, right? So how long would it take for you to get from A to B? 1 hour. That's obvious, right? And now you're saying, well, that's too slow. Let me drive a little bit fast. Let me drive 61 miles per hour. Okay, and then you guess, how long would it take for you to get there? What do you think? What's that?
Approximately 59 minutes.
That's a good approximation. That's what I do. I know it's not quite right. I know it's off by a little bit, but it's close, right? That's my feeling, right? So let's think about this. So from A to B, let's say, okay, suppose you drive from A to B. The distance is 60 miles. Okay, and your speed is equal to 60 miles per hour. All right. So given that, then so if it's 60 miles per hour, then your total time will be 1 hour, right? Okay. And now let's change it. Suppose the speed is now equal to 61 miles per hour. And you would think the time should now be 59, roughly speaking, 59 minutes. That's your intuition, right? And let's see if we can justify that. Okay? Yes. Okay. And let me also change it a little bit. Suppose if I change the problem a little bit, let's say, suppose your speed is let's say the distance is still 60. Suppose the distance is 60, and speed was originally at 30 miles per hour. And that's, well, how long would it take? That's an easy question, right? What do you think? 2 hours. Okay, we can answer that. Okay. Now let's say, okay, I wanna get that faster. Okay, let me change my speed to 31 miles per hour. What do you think? What would it be? What would be the time now? Okay, I'll leave it for you to think about that. It's an easy question. Okay. I always wonder that when I drive on a highway, sometimes. And now you can change this and one more. You can change the distance to 120 and change things around. Okay. I just make a few changes here. So instead of 60, you can say 120. And you can change that from 30 to something like, I don't want to put 120 here. I want to be too safe. I mean, you can put some. You can put some number. You can try 30, or you can try 60, or you can try 30, or you can try 90, and you can create new problems like this. Right? Let's see if we can use the differential to explain this. By the way, do you have a guess if it is 60 and 30 and 31, 30 to 31? How would that change? Is that obvious to us? Originally it was 2 hours. If you drive a little bit faster,
1 hour and 59 minutes.
1 hour 59 minutes.
Almost.
Yeah, almost 1 hour 59. Okay, we'll find out. So the guess seems to be 31. So you're gonna go 1 hour. Okay, 59 minutes. Do you agree on that? Let's find out. You don't agree, please.
Close enough.
What?
I thought it'd be 158 because you had an extra hour or
I
extra
see.
mile
You
per
think
hour.
it's probably 58 instead of 59. Yes? So maybe it's 58. All right, let's work this out. So how do we do this? Let's focus on the original problem here. Just do this one and forget about those variations for now. Right? What's going on here is that the distance remains to be the same. So d is 60 miles. Let's fix that. And we're changing the speed. Okay, therefore let's let x to be the speed, x to be the variable. Okay, so let's say we have distance equals to 60 miles, and x is the speed, and x is the independent variable. X changes. All right, and now what is the time in terms of x? The total time. I'm going to denote this by fx so that it looks like a function. All right? What should fx be in terms of x? 60 over x, right? That's a well-known formula in physics. Time is equal to distance divided by speed. Okay? And what we're essentially asking is that when speed is 61 miles, so first of all, f60, that's an easy one. That's just 60 over 60. That is 1. Everybody knows that. That's 1 hour, right? And we are basically asking what is f61 equal to, right? So that actually increase from 60 to 61. How will f change? Oh, that's exactly the situation we have over here, right? Therefore, let's apply the formula to this situation here. So, I'm going to erase this and just keep the box here. So, F61 should be approximately equal to, okay, so this is a question mark here. And we know by the formula, this is approximately equal to F60 plus F prime 60 times 1, right? 61 minus 1 is 1. We already know this is 1. We just have to compute the F prime 60. Okay? So what is F prime 60? Let's compute the F prime x first. What is F prime x? Simple. Minus 60 over x
Square.
squared. Right? Everybody see that? Either use quotient rule or use the power rule. It's easier to